Our next topic that we're going to discuss is the simple pendulum. Now, a simple pendulum is defined as the mass is concentrated at the end of the pendulum. And as we look at pendulums, we can see that they're going to give us a little bit of a problem, because we notice here the pendulum mass here at the end, and there's a force of tension along the string. We consider the string to be massless, and so there is the force due to gravity of the mass, and then we have the components, and the one we're interested in is going along this curve, and we can transpose that down here. And by geometry, this angle is theta, which means that this vector is the mass times gravity times the sine of theta. And so this is not linear. And that's where we have a problem. Now, to demonstrate how it looks if you were to have that pendulum go at a large rate, I've done a little calculation here. You can notice how this should be like a sine wave if it's related to Hooke's law, but it's a little bit, the peaks are just a little bit less pointy. And if we take the angle and go up even further, you can see how it's very, very not like a sine or a cosine. It's got these peaks aren't as pointed as we would think for a sine or a cosine. So we need to be able to deal with this. So let's put it here. Pendulums are not simple harmonic oscillators. Or we call that SHO, like springs. And that's because our force to restore is mass times gravity times the sine of theta. And theta is actually a function of t. Excuse me. So how do we get around this? How do we want to be able to examine or analyze this, but there is no simple solution to a differential equation that has a sine of theta t in one of the terms. But what we can do is a process called linearization. And what we do is we find where the sine function approximates a line. So let's take a look at the sine function. This is blown up quite a bit here. And you notice that from about this point to this point on the graph, from about negative 0.5 on the x-axis to about 0.5 on the x-axis, this line is fairly straight. Now, of course, these lines are pretty thick, but this area looks fairly straight. So we can try to approximate the sine as a function if we restrict the amount that the pendulum can swing down to a small angle. So when we do a linearization, we try to find a point where the sine approximates a line. This means that we limit the swing of the pendulum. And if we think about, let's say 15 degrees, that's about 0.2617, I'm taking this out a little bit far, 1799 radians. And if I take the sine of 0.261799, I get approximately 0.251899. So it's pretty close. So what we're going to do is we're going to limit our analysis to, say, about 10 degrees. So we'll let theta go from about negative 10 degrees to 10 degrees. That's where we're going to limit our swing of our pendulum. Now let's go back to our graph of the equation here, and let's put in 10 degrees. And you notice that now it looks a little more like a sine wave. So by limiting our angle at which the pendulum can swing, we get it back into something that looks like simple harmonic motion. So we've now taken this formula and we've approximated the sine of theta as just theta. And now we need to come up with a formula that's similar to Hooke's law. So let's go back to our picture of the pendulum, and I see I have this angle here, and I would like to get it in terms of x so that I can apply it to Hooke's law. And I notice that I have an arc length right here. And that arc length then, and from calculus, S is equal to the radius times the angle. Well, my radius here is just the length of the attached cord, and I know theta, and I want this x value, so I can say x, which is my arc length, is equal to L times theta, or theta is equal to x over L. So let's substitute that back into our function here. And remember, x is going to be a function of t, so we'll put mg x function of t divided by L, and it's this x function of t that I'm interested in. So I'm going to rewrite this as mg divided by L x function of t. And now I can apply Hooke's law. So Hooke's law was F equals negative kx function of t. And so this mg over L is very similar to k. So now we can use the basic formulas that we've had for the properties of a spring, and we can relate these to the properties of a pendulum by substituting mg over L into our formulas. Now omega was equal to the square root of k over m. Now let's substitute our value for k, that was mg over L, divided by m, and that just leaves me with the square root of g over L. Now what does this tell us? Well, it tells us that the omega value is independent of the mass. Doesn't matter what mass we put on the end, as long as it's within that 10 degrees plus or minus, the omega value will be the same no matter what. So mass does not affect the pendulum. Pendulums will say value of omega. Frequency can be calculated as omega is 2 pi times frequency. So we can solve for frequency and substitute in our values for omega, and the period is just 1 over the frequency, and that's 2 pi square root L over G. The formula that we use, since we're talking more about an angle, is theta function of t is equal to some theta max, that's our amplitude, times the cosine of omega t plus phi. So instead of using x function of t, we're going to transform that into theta function of t. And we can even take and use this formula in a lot of different ways. Later on we're going to talk about damping, and we can actually include damping into this formula. Fairly simple, and it'll be used quite a bit. You'll have a lab on pendulums, and one of the aspects is investigating this theta max. What happens when you get past that 10 degrees? How does it start to affect the measurements? So this is the simple pendulum. Next we'll look at the physical pendulum and see what the difference is between the two.